Let's take what will be for now a last look at the logistic equation y prime equals ky times L minus y, with the idea of looking at equilibrium solutions. What does equilibrium mean? Equilibrium means that the function isn't changing. When does a function y not change? It changes when its derivative, it doesn't change when its derivative is equal to 0. So that the condition y prime equals 0 is an equilibrium condition for this function. Now, if y prime equals 0, since y prime equals ky times L minus y, it follows that ky times L minus y is 0. And this occurs if y equals 0 or y equals L. And actually that's an if and only if. The only places this function is 0 are when y equals 0 and y equals L. Now, this function, ky times L minus y, is therefore equal to 0 at y equals 0 and y equals L. This means if we want to sketch a direction field, and I'll sketch this right next to, and I'll sketch it just above and just below the t-axis, but this function really, or these zeros of the slope, really do occur right on the axis. The direction field is therefore going to be horizontal because y prime is 0 and y prime equals 0 is equivalent to having a horizontal y versus t graph, a y versus t graph with a horizontal tangent at any of these points. Okay, and similarly at y equals L, the direction field is going to have to indicate slopes 0. Now, if we just think about y times L minus y, if that's multiplied out, it's quadratic. And it's quadratic with zeros at y equals 0 and y equals L. If we were going to draw a graph of this function, y times L minus y versus y, it would be a quadratic function with zeros at these points. A quadratic function has a parabolic graph. A parabolic graph with zeros at these points is going to maximize halfway between those zeros, so that at y equals L over 2, the slope field is going to reach a maximum. Okay, it's going to be as steep as it's going to be, and the actual slope is then going to end up being 1/4 k. And of course the actual slope depends on what k is. Here we'll just represent this by a line that appears to have a slope about 1, but the graph would be scaled so that this slope field would appear at this point to have slope 1. Now, at points in between, down here, the slope is going to be fairly small. And as we approach L, the slope is again going to get fairly small. So that this could be a rough representation of a slope field between y equals 0 and y equals L. We can also see, and we're not going to actually evaluate it, but if y is bigger than L, then this becomes negative. And the graph will then, of y versus t, will have a negative slope, and our slope field is going to start looking something like this. We're going to have negative slopes above the axis and greater negative slopes as we go not above the axis but above the y equals L line. We're going to have negative slopes, and they're going to get greater, and they're actually going to get greater pretty fast, so that by the time we get up to y equals 2L, this slope field is going to look almost vertical. This indicates that if we have an initial y value that's close to 0, now this isn't quite 0, so it does have some small slope, and eventually that slope is going to take it into higher values of y. The graph is going to get steeper, and then it's going to continue to get steeper. It's going to be steepest here. This is going to take it into higher y values rather quickly, but now the slopes are going to level off. That's going to give us our typical sigmoid solution to the differential equation, consistent with the analytical solutions that we've been looking at. And if y is greater than L, that's going to bring us down rather quickly, and we're going to approach the y equals L line, actually in a exponential fashion as we come back down. So we can say that the y equals L line is a stable point of stable equilibrium. We can go a little further than we have. If we happen to have a point on the y equals L line, let's just say our initial point is right here, or we could start at any point, of course. We could start at any time. Well, our slope is 0, so we're not going to go up or down. And when we get to our new point, slope is still going to be 0. We're still going to be on the line y equals L, indicating, and if we go just a little ways away from the y equals L line, we can see that the direction field is going to bring us into the y equals L line, so that L is going to be what we call a point of stable equilibrium. If we move a little ways away from a stable equilibrium point, we're going to come back to that stable equilibrium. If we start a little ways away from the line y equals L, we're going to come back to it, whether we're above it or below it. And the same, of course, is true if we start at 0. Now, if we're talking about a reproducing population, if you don't have any population at all, you're going to stay that way. You're going to have no population. But the y equals 0 population is not stable. If we come up a little above the y equals 0 population, then we do have some population, and we're going to assume that population occurs at least in reproducing pairs, that the smallest possible population is a reproducing pair, and that is then going to eventually lead to reproduction, new individuals, and the curve is going to start climbing, and it will eventually climb along a sigmoid path.